Thanks, yeah, and thanks also to the organizers, Marcus and Hussein. This, I think, has been a really exciting meeting. Lots of interesting talks, and in fact, lots of things that make my job easy because we've heard about some of the ideas I'm talking about. So this is an optically levitated microsphere, which Giorgio introduced nicely yesterday. I'll be talking about the kind of orthogonal sets of things we're thinking about doing with these systems, besides testing gravity at short distance, which we also think is important. I'm actually not in the vacuum chamber here. You're seeing a reflection off the window. This is a 20 micron sphere levitated in the center, and you're seeing it's levitated with near infrared light, and you're seeing some green light scattering off of it. So before I get to the actual talk, I just want to highlight the people actually doing the work. In the tradition of many people here, we're trying to be taken seriously by the high energy physicists. In fact, I sit in a high energy physics building, so they don't even know where to put our students on the spreadsheet if we don't have an acronym. So we're simple. This is our team, and we're collaborating with Giorgio's group on the gravity measurements, and I'll talk a little bit about some of the really interesting things in Jack Harris's group and levitating superfluid helium that might be interesting for fundamental physics. So I'm not going to belabor this because we've heard about it, but I just want to emphasize this incredible technology and optomechanical systems spanning many orders of magnitude in mass, and I think we'll hear even more in the next talk about this. And the thing that I think really excites me is that we know there's these huge problems with the standard model, or things that the standard model doesn't explain, even if it's self-consistent. And in many of the ways you might imagine addressing dark matter, dark energy, it's actually quite easy to get new forces. And in my past, I've worked on kind of standard WIMP direct detection for dark matter, but it seems like there's a whole orthogonal set of searches where instead of looking for a new particle, we look for a new interaction. And we might be able to see these new forces that have just evaded us to date because they appear at shorter distance or weaker couplings than we've been sensitive to yet. And these kind of optomechanical technologies, which there's far more expert people in the room than I, really open up new windows to try to answer some of these really hard and important questions in fundamental physics. So I'm going to be talking in particular about levitated optomechanical systems, so masses in the kind of picogram to milligram range. And again, we've heard about force sensing in general, or acceleration sensing with these sorts of optomechanical systems. I just want to highlight a couple things that I think are important, and others have highlighted at this meeting, but often, especially in the levitated optomechanics community, we tend to put up numbers about our force sensitivity, attonewtons and zeptonewtons. But for everything I'm talking about, and most of the things we think about and beyond the standard model of physics, really acceleration is the interesting, or force per mass sensitivity is the interesting figure of merit. This is true for gravity. It's going to be true for the tests of Coulomb's law and tests of the neutrality of matter that I'm focusing on in this talk. We're using the kind of simplest possible way to levitate these kind of 10 nanogram masses, at least in our opinion. We have a single vertically oriented laser, just like Ashkin had in the first trap in the 70s. We trap a dielectric microsphere just above the focus, and then we can apply an excitation. Giorgio talked about applying an oscillating gravitational field here to look for non-Newtonian forces. In this talk, I'm going to be focusing on applying electric fields to a neutral dielectric object and see what you see. The exciting thing here is that at the standard quantum limit for this kind of nanogram scale masses, you can get to acceleration sensitivities of order nano little g, Earth's little g per root hertz. We're not quite there yet, as I'll say, but we're within maybe 2 orders of magnitude of this now. In addition to the sensitivity, you're also electrically extremely well isolated, and for practical applications, this is really important. So here's the outline. I'll talk a little bit about our experimental setup and maybe some differences from what Giorgio showed in that we're really pushing on this acceleration sensitivity. We're trapping the largest objects we can with optical levitation. And then I'll talk about 2 applications in addition to what Giorgio talked about yesterday for Newton's law. So this is our experiment. It's really a tabletop scale experiment. The trap is formed in the vacuum chamber here, and we have some relatively simple optics. The nice features of this setup with the single low numerical aperture beam is we can position things around the trap, and we also use the minimum amount of laser power that we can to optically levitate this amount of mass. We're really only using photons to hold up against gravity, and we don't need more photons than that if we had a propagating trap or something. This is important, I'll show maybe on the next slide, due to heating of the particles in high vacuum. And we can essentially trap these things for infinite time. We've trapped single spheres for longer than a month at our current base pressure of 10⁻⁷ millibar until you turn off the lasers or drop a wrench on the table or something like this.
A brief question is without any feedback.
So this is with feedback. So Ashkin in his original paper did pump down some very high quality optical materials without feedback. We have also been able to do that, but you know, the laser pointing fluctuations heat it to hundreds of thousands of Kelvin. If you have a deep enough trap, that's okay, but it's not very good for precision measurements. So we turn on the feedback to cool it down. So one of the things, since we're interested in searches that scale with mass, or at least number of neutrons or number of nucleons in the spheres, we've looked in a bit to how large of a sphere you can easily optically trap, at least with the materials commercially available. So we've trapped spheres between 5 micron diameter, similar to what Giorgio was talking about, all the way up to 30 micron diameter silica spheres in this case, up to 30 nanogram masses. You know, you do need more laser power to trap these, but again, for the single beam trap, we're really just holding them up against gravity and not using more than that. And if we plot our acceleration sensitivity, so scaled into units of micro g, little g again is Earth's gravity per root hertz, versus the mass of the sphere, as is typical, you see better acceleration sensitivities when you go to these bigger masses. We've actually improved beyond this a bit, so what's limiting our acceleration sensitivity, I'll come back to this, is technical noise, basically from laser pointing fluctuations at the moment. We've now put all of those optics I showed on the previous plot into a vacuum, and that's actually gotten rid of some air-induced laser pointing noise, so we're now down closer to about 10 to the minus 7 little g per root hertz for these heavier masses. But the other nice thing is that you can have really long integration times. So here, integrating for 10 to the 4 seconds, you can get down to the nano g scale. So we're just showing here if we don't apply any external force and just average down what our acceleration sensitivity is, we really can get down to interesting sensitivities for the searches we're talking about. One thing just incidentally to note is that we've tried to go even bigger than these kind of 30 nanogram spheres. It turns out we can trap these 30 micron spheres at relatively high vacuum pressures, but as we go to lower pressures, we can sometimes keep the same sphere on the trap and watch the outer layers vaporize. So laser heating is causing these things to heat up to well above 1200 Kelvin or something like this, at which point you actually lose mass, and the laser, we see this also in the power needed to levitate them going down substantially. So this is an upper limit to the kind of current quality of silica. Giorgio pointed out this is really like Swiss cheese silica, not very high quality optical silica. So we're working on fabricating actually our own objects to trap with higher optical quality. I won't say too much about this. This is kind of a technical thing, but one of the nice things about working with the big spheres now is we can actually repeatably load in a deterministic way a single sphere into the trap. Lots of us in the levitated optomechanics community either spray these spheres into the vacuum chamber or drop them off a quartz cover slip. That's traditionally how we've done it. But now we can do, you know, as the biologists do in fluid-based optical tweezers. Here you're seeing a microscope image of one of these where it's sitting on a cover slip below the trap, and then you see it come out of focus when you actually pop it up into the trap, and we can lower the laser power and drop it back in that same place. So if we are able to make some high quality spheres or have one good sample, we can trap that same sphere over and over again. So as Mark has alluded to, once, in order to reduce kind of heating by the laser, and in our case we ascribe this to pointing noise of our laser, technical noise in the laser that's trapping the sphere, most of us use some active feedback cooling. And it's, unless you have a very deep trap, it's really essential below kind of millibar pressures to keep the sphere in the trap. So this is just showing the effect of this in our system. This is showing the power spectral density now in position instead of acceleration units, but they're just simply related by a factor in our usual plots. Here in meters per root hertz, at a relatively high pressure of millibar, where you see damped motion with the we have relatively low resonant frequencies because we're working with these massive objects at around 100 hertz. And this at higher pressure, it's consistent with the 300 Kelvin that we expect for the chamber temperature. Before we turn on the feedback, if we pump down and use the kind of minimum amount of feedback we roughly need to keep the sphere in the trap, we see the noise substantially decrease, of course, as you get rid of the gas damping. And as we turn up the damping more and more, we can substantially cool the motion of the sphere down to kind of 100 microkelvin at the highest gain we've applied here. And we actually aren't pushing down to the system noise yet and squashing just for kind of technical reasons, but again, we've we've improved a little beyond this. But you can get to effective temperatures, or really what we care about is acceleration sensitivity, but of course the temperature you can get to is related to the technical noise we have, substantially lower than you could hope in a kind of dilution fridge. And we heard about this earlier. It's easier to get there at low pressure than it is really by cooling things down. The other, I think, extremely nice thing about the levitated systems is that you can electrically neutralize the spheres. So we can just put two electrodes around the trap, apply an oscillating electric field, and correlate the motion of the sphere with that oscillating field. Then we flash it with UV light, and we can actually, depending how we do it, we can either knock electrons off the sphere or knock electrons from the gold electrodes surrounding the trap location onto the sphere. Here we're just showing that, where we're plotting the correlation in units of number of charges, and we can calibrate into single electron charges because we can nicely see correlated with these flashes of the xenon lamp, the UV light, which is the vertical lines here, these kind of discrete steps in the response of the sphere's motion to the electric field. So this is just the Millikan oil drop experiment done here in a kind of more precise way. The other extremely nice thing, though, is that once we turn this UV light off, we can get our charging rates or the currents flowing to the sphere down to something like 1 electron per week. So these are below yoctoamp currents, so the lowest SI unit for current. So this thing can be neutralized and then stay neutralized, so you're sure you have exactly the same number of protons and electrons on this nearly macroscopic object.
How do you know where 0 is?
Good. So in principle, you could be a bit wrong. I mean, you get the step from this. It turns out, though, that if you can crank up the field substantially here, and if you had even a single charge, it would push it out. The other piece of technology we need, Giorgio showed one way to do this, but we're also able to rotate the spheres in our trap, and this is really essential for controlling the electric dipole moments, as I'll come back to. So we're able to neutralize these spheres and get the monopole charge down to 0, but then we have dipoles and higher order multipole moments. It turns out, though, that even the amorphous silica spheres that, naively you wouldn't expect to be birefringent or to have much to change the polarization of the trapping light very much, because of the very low damping we have in ultra-high vacuum, or high vacuum conditions at least, you can spin these up to 10 megahertz just from their trace birefringence. So if we use circularly polarized light, something like a part in 10 to the 4 of that polarization is changed as it passes through the sphere, either through absorption or slight ellipticity, and over a day, there's a damping time of order a day. Over a day, that spins up to a terminal velocity of order 10 megahertz. With more birefringent things, we can actually go faster. The challenge, though, is that things blow up as you start to spin them faster than 10 megahertz just from centrifugal stress. So one of the main challenges with more birefringent materials is just keeping them from jumping out of our feedback loop and spinning up and blowing up. But it turns out just very kind of luckily and conveniently, these non-birefringent particles spin right to about where we want them, just below the centrifugal stress limit for these larger spheres. And I should say that after this, actually very recently after we showed this for the larger spheres, by going to smaller objects you can spin even faster before they blow up, so there's actually been gigahertz speed rotation demonstrated for 100 nanometer scale objects. Okay, so this is the kind of technology, so what can we do with it? So I'll talk about kind of 2 applications. And the first is really, now that we know we have this object with exactly the same number of electrons and protons, how neutral is it? And the motivation here is kind of twofold. One is really related to cosmology and dark matter models. And the kind of story here is that we often, when we talk about dark matter, 80% of the matter in the universe, we say, well, we add one new particle to the standard model, a WIMP or an axion, with essentially no new interactions. But the 20% of matter we do know about is much more complicated than that. We have 3 families of fermions with 4 fundamental gauge interactions. So it's not clear why the dark matter, which is most of the matter in the universe, should be so simple. Or at least naively, you might want to think about whether dark matter is really so simple. And as we relax these maximally simplistic dark matter models, it's quite easy to start adding new forces that the dark matter is charged under. The standard model can't be charged under that because, of course, we know dark matter interacts very weakly with us. But there's nothing that prohibits the dark matter from having new fundamental interactions. And then naturally, you can write down a weak mixing between the dark sector and the standard model. So this kind of kinetic mixing shows up in the Lagrangian level. So we should be able to maybe detect these forces in a hidden sector through their weak mixing with the standard model. And In terms of what that would look like to us is that maybe the dark matter has something like a dark photon that it interacts with. That dark photon weakly mixes with the standard model photon, and then those dark matter particles pick up a tiny electric charge under standard model electromagnetism. So these go by the name of millicharged dark matter particles, although they could have microcharges or nanocharges. This coupling has to be much smaller than 1, but there's no preferred value for it, unfortunately, so we don't really know where to look, but want to look where we can. Lots of people have looked for these sorts of millicharged particles before. This is a kind of somewhat older review plot, but showing exclusions on the log of the coupling versus the mass, many orders of magnitude here on both axes. Below the electron mass, there's really strong astrophysical constraints. But as you go to higher and higher masses, and especially GeV and above the reach of accelerator experiments, there's actually allowed parameter space even for dark matter particles or millicharged particles with true millicharges, or even 10th or 100th of a charge. And there's actually been some recent interest in this window by people here at CFA and elsewhere to try to explain this edges signal where there's an anomalously low temperature apparently observed for the neutral hydrogen in the early universe. Maybe that hydrogen got cooled down by coupling to the cold bath of dark matter around that time. To make enough coupling, though, you need to do something like give the dark matter a millicharge. So people have been thinking about this a lot. The other major reason, I think, to test the neutrality, besides this dark matter motivation, or related to it, is the kind of interesting fact that we've measured that the electron and proton have equal and opposite charges to a part in 10 to the 21. That might not strike you as surprising, since we all know they're equal and opposite, but that's really an experimental fact, and there's no fundamental underlying deep symmetry in the standard model that guarantees the quarks and the leptons should have equal and opposite charges. There's some arguments from gauge anomaly cancellations that, if we knew the full content of all the charges in the standard model, there's some rules about how they have to add up. But that, in the absence of a clear symmetry guaranteeing this, this is kind of model dependent, and it's also sensitive to new physics. So for instance, if I do anything that gives you a new tiny millicharged particle or something like this, if I give the neutrino a charge, small photon mass, or a new force that couples to baryon minus lepton number, as Eric was talking about, and this is kind of a natural extension of the standard model because it's something you can charge in the standard model without violating any symmetries, you actually would expect this to maybe show up in tiny deviations of the electron and proton charge. So if we could measure, this is a really fundamental thing that if we could measure better, we'd like to. The challenge, of course, is that we know it's equal and opposite to a part in 10 to the 21, so it's not so easy to do better. And in fact, if you look in the particle data group tables, this has been kind of where we've been stuck as a community in the precision metrology community since the 70s. So we haven't dramatically improved measurements of the neutrality of matter in something like 45 years. And similar story for neutron charge, where the best limit, even though there's been a couple attempts to do better, the best limit still comes from the late 80s. So we're hoping optomechanical systems might provide some new technique. I'll just quickly go over the previous searches in matter, what we've done in the past for searching for kind of fractional charges or millicharge in matter, as well as matter neutrality. So the most recent search for fractional charges was this automated version of the Millikan oil drop experiment done by Marty Pearl's group at SLAC in 2007. It's really an impressive experiment. They tested 40 million oil drops. In some cases, they even suspended pieces of lunar dust in the oil drops to look for strangelets and things like this. But they found, this is on a log scale, this is a histogram of the charges they measure. It's very Gaussian, and they don't, in their case, they were looking for free quarks, so they don't see anything out here at charge of a third. But they designed the experiment only to be sensitive down to about 1/10 of an electron, so they wouldn't be sensitive to these single millicharge particles. For matter neutrality, there's kind of two most sensitive techniques, these acoustic resonators, where you put a neutral gas in a spherical electrode, you apply an oscillating electric field and actually look for collective motion of that gas. The first experiment was done in the 70s. It was probably flawed and got too strong of a limit, so the more recent experiments haven't gone beyond it. There's also the famous neutron beam deflection experiment from the late 80s, where you just shoot neutrons through an electric field and look at their deflection. And kind of interestingly, both of these end up apparently systematics limited at the kind of 10 to the minus 21 electron level. So they seem to see something just about this sensitivity, and it's not obvious you can push forward with the same techniques. The nice thing about levitated objects for these searches is that we can fully avoid the backgrounds that plague this acoustic resonator technique from free charge. So we know we have exactly the same number of electrons and protons. We don't have any charges flowing to the sphere, while at the same time maintaining relatively large masses. And by large here, I mean something like 10 nanograms for the optically levitated spheres. And I'll highlight for magnetically levitated superfluid helium, maybe up to milligram masses. And we can also, as we've heard about, maybe exploit some of these exciting new technologies for optomechanical readout of the forces acting on these objects. So we did an initial search now several years ago. You just neutralize the microsphere as I described. This is again the same plot I showed. We're showing the response, the correlated motion of the sphere in the direction of the electric field versus time. We discharge the sphere at the beginning. We crank up the electric field substantially and then zoom in on the inset here on the response. We integrate overnight and then look for any net force on the sphere that could be consistent with a residual charge. So we look for any offset in this data from exactly zero response. In this case, we repeated it for 10 microspheres with a total mass of 1 nanogram, so 5 micron diameter spheres. We actually did see a statistically significant response, but the direction of that response was perpendicular to the electric field rather in the direction of the electric field. So it was consistent with forces on the electric dipole moments of the spheres, not on a net charge. So that's a systematic that limited this previous search, but we could still set limits on the abundance of such particles bound in the spheres versus their fractional charges. The blue and the red here are showing the free quark searches. So they test much lower abundances because they test more mass, but only down to about 1/10 of an electron. And with the levitated objects, we can go down to much smaller fractional charges, although not as far on the abundance axis. So if you want to do better, the thing to do is to improve the electric dipole backgrounds and higher order multipole backgrounds. So we basically in the first search, we didn't do anything. We just took that as a systematic. But if we wanted to get rid of forces on the microsphere due to these electric dipole moments, we have a couple handles. So of course the force looks like something like the dipole moment couples to the gradient in the electric field. So if we can make that gradient zero, then we can get rid of the net force on the sphere. And the total dipole moment of the sphere comes from two things. First, there's a permanent dipole moment that Giorgio discussed yesterday, just in the 10 to the 14 to 10 to the 16 charges in the sphere. Something like in these larger spheres, 1,000 electrons are offset by order of micron from the center of that charge distribution, and this is a permanent moment. This is our main background, since if we apply an oscillating electric field, this oscillates at the same frequency as our signal would. But we also have this nice handle that the sphere is polarizable, so we should get a force also at twice the applied oscillating electric field frequency, and we can make that relatively large by working at high fields. So here we're just showing a measurement of the force on this sphere versus the amplitude of our electric field. You see this quadratic response at twice the drive frequency and the linear response at omega. We can use this twice frequency response actually though to zero the gradient at the location of the microsphere, because both of these terms couple to the same gradient of the electric field. We can make the red curve zero, and then we're guaranteed that the blue curve is also zero. So this is a nice handle. In the first version of this, the way we did this was just to make one of the electrodes semi-transparent 20 nanometer thick gold electrode. Nothing too fancy. We could just shine an alignment beam through there and then align the plates to kind of 100 microradian precision initially, and then tilt them around until we could zero this 2 omega response. So I'll show the data on that on the next slide. The other thing that was really crucial to make this work, though, that I alluded to at the beginning, was we're now able to spin these spheres. And when we first started trying to do this, basically the permanent dipoles were flopping over, aligning with the electric field as we oscillated it back and forth. And because the spheres are a little bit aspherical, that looked like a large apparent motion of the sphere, even if the net force was zero, because we had made the gradient exactly zero. Just the torque on the sphere flopping it back and forth causes a large apparent background. But now, because we're able to spin these much faster than megahertz in the vertical direction, you average over the dipole moment in the directions other than the spin axis. So you have the permanent dipole moment only pointing up, but you also have a very large angular momentum, so that the torque on the sphere only causes a little bit of precession and doesn't cause it to flop over and cause this apparent background. So once we start to spin these things, we see a huge background go away.
And this is also the way you read it out, the little precession?
Yeah,
Get a
so
signal from that,
yeah, we do get signal from the precession. In this case, when we're spinning them very fast, we don't see it, but as the thing is spinning slowly, you also see the free precession of the spinning top as it spins up, and you see it scale with the spin frequency as you expect. So just because, either through a little bit of absorption or a little bit of asphericity, we can see the spinning in the polarization transmitted by the sphere.
even above megahertz.
Yeah, even above a megahertz, yeah. So we can go then and try to do an improved measurement relative to that initial search. Now taking care of these dipole moments, backgrounds arising from these dipole moments. So this is showing some of the data we've taken with the existing system. So sorry, this is a complicated plot, but on the left in the blue here are the response at the drive frequency. So where we'd expect to see a signal on the X direction, the direction of our electric field, and Y and Z just to see the other directions. These help us know about other forces that could be arising from gradients. And also at 2F, and the x-axis here is the tilt angle of our plate. So as a reminder, we can tilt our electrode until we can zero the gradient in the electric field, and at some point the gradient should be zero, and we should also have no background in the blue points in our signal. We have this nice feature, though, that now that we control the electric dipole moment, it's pointing in the z direction. Because of the curl of the electric field is zero, dz by dx is equal to dx by dz. This is the term that would affect our force in the x direction. Whereas this one we can actually measure from the 2f, the induced response in the direction of the electric field here in the z direction. And in fact, this is very consistent with the dipole only pointing in the z direction because we see a large change in the force response that goes through zero on this 2f, and we can find the point exactly where it goes through zero. On that point, we would hope actually that our signal at the drive frequency would actually go through zero. So it's quite good. So this is scaled actually into neutrality of matter units. So we've divided by the number of charges in the sphere. So this tells us that the response is actually very inconsistent with zero and consistent with a net charge or a net difference in the electron and proton charge of something like 10 to the minus 20 electrons. We don't think this is real, unfortunately, but there is still a systematic background. But the other nice thing, this is within one order of magnitude of the world's best previous test of the neutrality of matter, but the sensitivity is at those limits, right? So the error bar is about a factor of 10 smaller than this background. If we could get rid of this background, we would be at, with a single sphere, we'd already be at the best previous sensitivity, and hopefully we could push beyond by integrating it a little bit longer. So we need to get rid of this background. It turns out, though, that this is a background that has been challenging us for a while, but it does also appear to be there without the sphere. So we can't claim it's a non-neutrality of matter. Initially, there was some electrical pickup. We fixed that, and then we also see actually in this initial version where you have the electrodes on alignment stages, there's a small electrostatic force between those electrodes, which is moving the electrode on this kind of floppy stage where there's the spring is a little bit floppy there, so you can actually move the electrodes substantially enough that you induce vibrations in the lens, holding making the trapping laser, and that causes us to pick up an apparent background even without the sphere. So we've now redesigned this whole thing with much more rigid electrode supports, and instead of trying to just tilt the electrode to minimize the gradients, we're applying trim we have electrodes to trim the field. So we're hoping that we can get rid of this unsatisfying background, but currently we're actually already improving somewhat over previous searches for newly charged particles. Let me just say one more thing before I show you what that translates into in terms of sensitivity. So in parallel to our group at Yale, actually Jack Harris's group at Yale is another levitated optomechanics group in the same hallway, and they've recently demonstrated this really impressive thing that they can levitate and do optomechanics with, for the moment, kind of 500 micron scale superfluid helium-4 droplets. They can couple to these droplets to whisper and gallery optical modes in the droplets, and also read out mechanical modes, surface modes of the sloshing of the droplet. And this is actually a really nice system for these neutrality of matter tests because as far as real materials go, superfluid helium is one of the kind of nicest, purest real materials. It has no intrinsic charge disorder, so this issue with dipole moments that we see in the silica spheres should be much less of a problem, if a problem at all. You can get very large masses, so lots of nucleons in a kind of millimeter to centimeter scale drop. They're still working on this, but they expect to be able to get these kind of masses eventually. The thing's naturally cooled from evaporative cooling to hundreds of millikelvin, and you can access, as I said, these surface modes. And they actually understand very well the surface modes they see. There's some more references here if people are interested. But this could be a nice system, and they're installing electrodes now to try to also do this kind of neutrality of matter test with levitated superfluid droplets. So again, these are somewhat complicated plots, but let me just show what our sensitivity looks like and where we hope to be hopefully very soon. So these are the corresponding constraints on the abundance of millily charged particles versus their fractional charge from the data I just showed, where we had this non-zero background. Our previous search here is in blue, and the free quark search is here. Already just taking the background we saw as a systematic limit to the sensitivity, you would go something like with a single sphere, you'd actually already go an order of magnitude in abundance. It's 10 times heavier than the 10 we tested before. We can also test 10 more and push a little further down. And if we could get rid of this background, we'd push another order of magnitude in sensitivity to fractional charge. For the liquid helium, if you put in the same sorts of numbers, you can test even further down on the abundance axis. So this is many orders of magnitude here on this axis. But not test quite as far down in fractional charge because the objects are much heavier. If you translate this into constraints on the neutrality of matter, so this is the signed sum of the proton and electron charge, so it can either be positive or negative, but I'm trying to show it on a log plot here. So there's an axis cut in the center versus the neutron charge. Of course, if charge is conserved, as in beta decay, for instance, this would collapse to a one-dimensional parameter space, but being maximally agnostic for the minute, you have a 2D parameter space. The kind of neutron charge measurements then show up as this vertical line, and the proton plus electron charge measurements show up as these kind of diagonal lines, which look like a box on this log plot. Our existing results, as I said, with the background we have, are about an order of magnitude from the best existing sensitivity, but if we could get rid of this background, which we really think we can, we'd already be beyond the best existing sensitivity, and hopefully could even go a bit beyond. As I said, our acceleration sensitivity is a bit better now. With liquid helium, because you have lots of nucleons, you can go even maybe a couple of orders of magnitude beyond. And again, these are both limits that haven't been improved in kind of 40-ish years. So if we could do this, we'd be quite happy. Okay, so I think I still have a few minutes, so let me just quickly talk about some other planned work. So this is what we've been working on in the recent times, other than the gravity searches Giorgio talked about. But we also just like you can test Newton's law at short distance, we'd like to test Coulomb's law in a new generation of tests, eventually down to micron distances. The motivation is very similar to what I said before. If there's a hidden sector with a new gauge force in that hidden sector, for instance, the prototypical dark photon, you can have that mix with standard model photons and get a small correction to Coulomb's law. Just looks a lot, if you remember what the Yukawa like modification to Newton's law looks like. Get the same thing for Coulomb's law, where you get some small coupling chi, in this case it's chi squared, and some exponential term that falls off with a length scale corresponding to the inverse mass of that dark photon. And this is somewhat generic mechanisms, and we can search for a wide variety of these sorts of new hidden sector dark matter models by perhaps doing better tests of Coulomb's law than we have in the past. There was a previous set of laboratory tests that searched for deviations from Coulomb's law. If you actually go to the first chapter of Jackson, you'll see this picture there. This was a test in the 70s, but more recent ones as late as the late 80s. And these were looking for a non-zero photon mass, but they actually still show up on the dark photon laboratory constraints plots as some of the most sensitive laboratory tests, kind of in the micro EV mass range, which corresponds to the 10 centimeter scale of the devices. We hope with microspheres to be able to go to micron sorts of distances, as I said, or EV mass scales. I'll just go quickly through this, but just to show you roughly what you might expect to be able to do with these sorts of force sensors and microspheres. So the idea is to position a highly charged microsphere instead of a neutral microsphere, a very highly charged microsphere outside of a large electric field. So you have a large electric field between these conductors that, when Coulomb's law holds exactly, is completely screened by the shielding conductor. However, if you have a dark photon or some sort of new physics that gives you a new gauge force in the dark sector. You can get this field essentially leaking out of the perfect shield, so the charge that's induced on this shield is not fully screened due to the length scale of the mass corresponding to the inverse mass of that dark photon. So you'd see some exponential leakage of that field, which the microsphere could sense as a very sensitive electrometer. This is nice. It's complementary to some of the other searches of dark photons. This is almost like a light shining through wall experiment because you're making the dark photons right here in the lab. They don't need to be the background dark matter, but we can still maybe be competitive with some of the parameter space for dark photons. So for experts who have seen this plot before, this is, again, many orders of magnitude uncoupling versus mass of the dark photon. The dark green regions here are the best laboratory constraints. There are some strong astrophysical constraints, somewhat model dependent, but relatively robust astrophysical constraints. And then this Coulomb region here is actually just what I was talking about, that picture from the beginning of Jackson, showing the previous version of Coulomb's law tests. That's over here. If you go to shorter distances and larger masses with the sensitivity we expect, and maybe ultimately at the standard quantum limit, you might be able to push a couple orders of magnitude down below the previous best experiments for these masses of dark photons. So this is a tiny slice of some much bigger parameter space, but maybe comes for free essentially if you can excite the microsphere in a slightly different way than we are in the gravity and other searches. Okay, so that's all. I'll just conclude there. I'll say I think this is still, very much an exciting time in figuring out what we can do with these sorts of optically levitated objects. I showed a couple applications, but we heard from Jake and lots of other people at this meeting about new ideas for optical mechanical sensors for dark matter and other really interesting things in cosmology. So we're hoping that this really is just the beginning of a lot of really interesting searches. So, thanks.
Thanks a lot, David.
So are there any constraints you can put on the baryon minus lepton number kind of coupling to dark matter?
Yeah, so actually an interesting thing in this electrical, this kind of large electric field would be to put two different spheres with different neutron numbers. Yeah.
Like two different materials or something?
Yeah, so we are setting up a tweezer array, and we can put two different neutron number spheres. Just like there should be, if you have a new force that couples to B minus L, it's also likely to kinetically mix with the photon. So you would also see those spheres be pushed on a little bit differently by the electric field we're using here. So you would put those here. You'd also put those next to the mass attractors Giorgio was talking about and look for a scalar type interaction. So this is maybe a bit down the line, but yeah, definitely. Mm-hmm.
So in your this extra background that you have due to the lens shaking, right?
Mm-hmm.
So if you just have a very good vibrational sensor, like can
Yeah.
you use some kind of feed forward to just
Yeah, so the trick here is that just to resolve this background, it takes many hours. It's a bit like what John was discussing with Acme, where you can fix the backgrounds you see quite easily, but the ones that you have to integrate a while to see, in principle, yes, but in practice, they're kind of hard to fix that way. So we just tried to redesign everything to get rid of the vibration. At some point, if you couldn't get rid of it, you could try to understand it and do this.
In a similar vein, if do you have any sense of what your acceleration noise flow would be if you turn the laser off for a period of free fall and then recapture?
Yeah, I think you could basically read it off this curve. So it's kind of at the 10 to the minus 8 little g per root hertz level. We haven't tried it though.
Do you know what the limit is to that 10 minus 8?
Yeah, so not yet at the shot noise limit of the readout. Still, that's the kind of system noise of our sensor, which we haven't pushed on because we have technical noise in the pointing. Yeah.
What's the
Let's see. If I think of my intentionally charged particle as an electrometer, is it worthwhile or interesting to specify its sensitivity in sort of electrons per root hertz?
Yeah, I think it is. It's probably not the world's best electrometer, but it's an and you know, ions might be good for some of these dark photon tests in a very similar way. I could convert it. It depends a little how much charge you can get on the sphere, but we think for reasonable numbers, other people have been thinking about how much charge you can get on these spheres. You can get something like 10 to the 5 or 10 to the 6 electron charges on this size of sphere. I can give you the number offline for what it corresponds to. I think the trapped ions, though, are going to be a bit better, and then it's a question of how you can engineer your experiment and, you know, make all that sensitivity. The other advantage we have is that this is a micron scale object, and we can get it microns away from a surface, which may or may not, could also be true for trapped ions.
So what's the maximum number of charges you can put on these spheres?
Yeah, so James Millen's been thinking about this quite a bit for the Paul trapping. We've seen charges as high as 10 to the 5 electrons. He's seen 10 to the 5 electrons now, though, on nanospheres. So if you really push this, in principle, if you had an alpha source or something and you really whacked at this, you could charge it to kind of, you know, megavolts, and then you'd have, on this size sphere, even more than 10 to the 6 charges.
How precisely can you control the angular velocity?
Yeah, so we're working on doing this better. So for now, we just kind of let it spin to, well, actually, maybe I took this slide out, but we do have a little simple active feedback loop, and we can control the velocity to a part in 10 to the 7. So it's spinning at kind of megahertz, and we can control the rotational speed to subhertz. People have done better, though, with kind of rotors that they can lock to a rotating circular polarization in Marcus Arndt's group. So it's not limited by the kind of gas damping in the system, it's limited just by our silly feedback system. To do it better here, we'd like to have spheres we could apply larger torques to, so truly birefringent spheres. We've grown some of those spheres out of this calcite-like crystal, spherical crystal, but it has too much heating absorption of the laser. So we're now trying to fabricate out of single crystal quartz some cylinders we can trap.
Okay. David, thanks a lot.
Thank you.